Hello everyone. Today I'm going to show you the simulation and working of fast Fourier transform on MATLAB, and the version of MATLAB that I'll be using is the 2019 version. So basically FFT or fast Fourier transform is a method which is used to convert a time domain signal into a frequency domain signal. Here, I am taking a time domain sinusoidal signal which has time on its x-axis and amplitude on its y-axis. And suppose we want to know the frequency of the signal, then how do we do that? Then we use a fast Fourier transform and we get this frequency domain signal. We get this signal and you can see that one peak that is visible, and you may ask that why is there only one peak that is visible? This is because we are using only one frequency and therefore only one peak is visible. Now, suppose that we add some noise to the signal. This red zigzag pattern signifies that we have added some noise to the sinusoidal signal. Then when we apply fast Fourier transform, you can see that there is another peak including the earlier peak. This peak with frequency higher than this peak is termed as FH, and the other one is termed as FL with the low frequency. So now you can see that there are two peaks that are visible. So now let's just say that we want to know the original signal. Then how do we do that? Then we pass this signal through a low band pass filter which will eliminate this high frequency signal, and we'll get only this FL in the output, and then we'll apply inverse fast Fourier transform on this signal to get back the original signal. So this was all about the basics of a fast Fourier transform and what it does to a signal. So let's now jump into the simulation part of this circuit. Here you can see that I've made this code. Let's understand what I've done here. Here we have taken fs to be some sampling frequency, and we have taken the value to be 1000 hertz. Then ts is 1 by fs, which is basically the sampling period. Okay, then now we have dt, which gives us the duration and starts from 0, and time from one sample to the other is ts, and for one sample let's take the duration to be 5 minus ts, which is 5 seconds minus ts. Then we have taken three frequencies, f1, f2 and f3, and we have added some random values of this frequency. For f1 we have added 10 hertz, f2 is 30, f3 is 70. Then y1, y2 and y3, these are the sinusoidal equations. So basically 10 signifies the amplitude of the signal, then we have sine, and then 2 into pi is 3.14. f1 is the frequency corresponding to this signal, and dt is the time period. So basically it is the sinusoidal equation of a signal having an amplitude of 10 and frequency f1 and a time period of dt. Then we have y2 for f2, then we have y3 for f3. Then y4 is y1, y2, y3, which is the sum total of all the three signals. Okay, so let's now take a variable nfft, which will give us the length of y4, which is the sum total of y1, y2 and y3. Now for a good resolution, the number of length of signal must always be equal to the second power of length of signal. Therefore nfft2 is another variable that we have taken, which is equal to 2 times power of next power 2 nfft. Then we are taking another variable ff, which will do the fast Fourier transform, where y4 is the signal we want to perform fast Fourier transform on, nf52 is the length. Then we have taken another variable fff, which will basically lead the symmetrical part of the peak. Okay, the last statement is plot absolute fff, which will give us the magnitude of fff. Let's now run this code. As you can see that there are three peaks that are visible. This is the frequency, this is the amplitude. So this gives us the fast Fourier transform of the signal, and we get three peaks for the three signals, as I showed you over here, that we get one peak for every one frequency, and we have three frequency, hence we are getting three peaks. That's all for this fast Fourier transform. Thank you for watching this video.